Rectangular coordinate system is particularly useful to describe the two-dimensional motion of a particle in cases where the particle is doing a motion in such a way which can be divided or decomposed into two perpendicular components, right. So we know that generally the x and y axis, their directions are described by unit vectors I and j respectively. In my handwritten notes you will see I with a cap on top, similarly j with a cap on top, representing the directions in x and y respectively. They have a length equal to 1 in the particular unit system which you are using. So their length can be 1 meters if you are using SI system and 1 feet if you are using the US system, right. Here you can see that if for example r is a particular vector describing the location of a particle at point A, this r can be written as a sum of its x component which will be x times I and the y component which will be y times j, right. X and y without bold symbol are representing the magnitudes of x and y components of a position vector, right. So small x and small y are the magnitudes of the x and y components of that r vector, and I and j are the directions of those two components. Similarly, the velocity at point A will be tangent to the path, and that velocity again can be described as a sum of Vx and Vy. Each of Vx and Vy are also vectors, but one is in x direction, one is in y direction. So it means that rectangular coordinates will give us an opportunity to describe any of these three vectors r, v and a in terms of its x and y components. Similarly, you can see acceleration will be having some direction which will be neither tangent nor normal to the path, but again whatever that direction is, we can describe it as a sum of ax and ay, right, and that sum is a vector sum, right. So ax and ay both are the vectors and their directions are I and j respectively. The vector representation of r, v and a, the position vector, velocity vector and acceleration vector can be described or written in terms of their x and y components. So we know that r is x times I plus y times j, where x and y are the magnitudes of the x and y components of that r vector, right. If we take the first derivative of r with respect to time, so let me take the first derivative of r vector with respect to time, it will simply become dx by dt times the I vector plus d of I vector with dt times x, right. Similarly, the second term will become dy by dt times j vector plus d of j vector by dt times y, right. And the point here is that the derivatives of I and j vectors with respect to time will be 0, because they have a constant magnitude and a constant direction, right. So I and j are the vectors in which neither the magnitude nor the direction is changing with time, so their derivative with respect to time should be 0. So therefore this term will become 0. Similarly, this last term will also become 0, and let us represent dx by dt as x dot times I vector. Similarly, this dy by dt will become y dot in our notation times j vector, right. So and the first derivative of r vector with respect to time is actually the velocity vector, right. So we get this second expression, x dot and y dot are the first derivative of the magnitude of x and y components of the position vector with respect to time. We can repeat that exercise one more time and we can get a third equation, that acceleration is the first derivative of velocity vector with respect to time, or the second derivative of position vector with respect to time, and that will actually become x double dot, a scalar quantity, times I vector, plus y double dot, a scalar quantity, times j vector, right. So, if I clearly write here what is x and y, they are actually the magnitudes of the x and y components, of the position vector, right, of position vector r, right. Similarly, what will be x dot now? It will be the magnitude of the x component of velocity vector, right. Y dot will be the magnitude of y component of velocity vector. Same goes for the x double dot and y double dot. X double dot will be the magnitude of x component of acceleration vector, and y double dot will be the magnitude of the y component of acceleration vector, right. So, let me also write it in a slightly different notation. X dot will be sometimes represented by v sub x, right. V sub x means the x component of the velocity, right, but it is a scalar quantity. So, magnitude of the x component of velocity vector. Similarly, y dot will become v sub y, I will write it sometimes as v sub y, but it is a scalar quantity representing the y component, magnitude of the y component of velocity, right. Same thing for x double dot, I will be actually using a symbol a sub x. For y double dot, I will be using a symbol a sub y, right. So, if we simply apply basic trigonometric identities here, we know what is sine of theta, where theta is actually the angle between x axis and the vector. We know what is cos theta, right. So, sin theta will actually become Vy over V. Similarly, in this case cos theta will become Vx over V, and tan theta will become Vy over Vx, right, Vy over Vx. Similarly, we also know that sin square theta plus cos square theta is equal to 1. So, when we apply all these trigonometric identities, we will get these scalar relationships which we will be using again and again in the problems in this topic. So, we know now that V square is equal to Vx square plus Vy square, right, using this identity. Similarly, if we have x component Vx, it will become V times cos theta, y component will become V times sin theta. Same can be applied to the acceleration. We can describe it as a sum of its x component and y component, and the magnitude of A will be simply a x square plus a y square square root, right. So, all of these scalar relationships you might know already, but we will be using them now to describe our curvilinear motion, right. Now, what types of problems which you might expect in this whole topic? Let us discuss something about that. If, for example, consider the first case when x is given to you as some function of time f1 of t, right, and again remember what is x? X is actually the magnitude of x component of the position vector r. So, please keep these three equations in mind. Small x, right, is the magnitude of x component of the position vector r. Let us say that you are given that x as a function of time, and y is also given separately as another function of time f2 of t, right, f2 of t. So, now it is like a particle is moving in curved direction, it is following, for example, this orange path, this path, but the x component variation with respect to time is separately given to you as this function, and the variation of y component of that particle or that position vector of that particle is given to you separately as a function of time, right. So, the x quantity as a function of time is separately given, y quantity separately as a function of time is given, right. First thing you can do with this information is that you eliminate t from both equations. For example, determine t from the right equation and put in terms of y in the x equation, right. So, the very first thing you can do from this is eliminate t from both equations, right, from these equations. How you can do that? For example, determine t as a function of y and put it in the first equation. So, you will be getting a equation between x and y, right. So, for example, you will be resulting in an equation, for example, y is equal to some f of x, right, or x is equal to some f of y. You can eliminate t to get a relationship between x and y. What that relationship will be actually graphically? It is the equation of that orange line, it is the equation of path, right. It will tell us what will be y for any x, right, y for any x. So, it is actually the equation of a path. This is y is equal to f of. So, y is equal to f of x is the equation for path, right. So, whenever you are given in this particular problem type two independent functions describing x and y components of a motion, one thing you can readily do with that is to just merge these two equations, combine them and get the equation of the path, right. So, all such questions in which these relationships are given and ask you to plot the motion or visualize the motion, all will be solved by this technique, by simply combining both x and y to get a combined equation. Now, let us move forward and let us see what else you can do with these given relationships of x and y as functions of time. What you can do now is that you take first derivative of x with respect to time. So, dx by dt will actually become d of f1 of t with respect to time, right. So, the function in time can be differentiated with respect to time, and what this differential or this differentiation should give you, it should actually become v sub s x, right, in scalar. So, this derivative is actually the magnitude of the x component of velocity, right. Similarly, I can do same thing with dy by dx dt actually, it will become d of f2 of t by dt, and this will become the v sub y, which is the magnitude of the y component of velocity, right. So, actually this, when you evaluate this differentiation, you will be describing Vx as a function of time, right, as some function of time. So, it will be some function of time. Similarly, here it will give you, this differentiation will give you Vy as some function of time, right. One thing now you can do is that if you are asked to determine velocity at a particular time by giving you this information on top, you can now determine that velocity, because Vx and Vy are known at a given time. You can simply write the total V vector as Vx times I plus Vy times j, right. So, at any time instant, if the velocity is to be determined, simply take the first derivative of x given to you as a function of time, take the derivative of y given to you as a function of time, put that value of time in those equations to get the x and y components of velocity at that time, and then write it in the vector form like this, right. Similarly, if you were asked to determine the position vector at a particular time, You already have the x as a function of time, y as a function of time. Just put the time directly in that, and you can write position vector r as x times I plus y times j, right, where x and y are the constant values of the x and y components of position vector at a particular time, right. Same as the Vx and Vy are the constant values which are the x and y components of velocity at a particular time. We can continue that exercise and we can also determine second derivative. For example, we can take d over dt of Vx, and this will actually be a sub x, right. Similarly, we can take d over dt of Vy, and this will become a sub y, right. So, all the questions like what will be the acceleration vector at a particular time, how you can evaluate that? Simply take double derivative of x, you get actually ax as a function of time, right. Similarly, take double derivative of y, you get ay as function of time, right. So, put that value of t which is given to you to get fixed constants ax and ay, and finally write the a vector as ax times I plus ay times j, right. So, you can determine the acceleration vector this way at any given time instant, right. Similarly, another type of problem could be when acceleration is given to you in both x and y components independently as a function of time, right. For example, some a sub x is given to you as a function of time, let us call it as g1 of t, right, and a sub y, for example, given to you as a function of time, right. So, this information is, let us say, given, and you are asked to determine velocity vector at a particular time, position vector at a particular time. What you should do? You should integrate both components separately, right. So, for example, you should integrate ax with respect to t, and that should give you Vx, right. So, Vx will be again as a function of time. So, this should be actually g1 of t dt is equal to Vx, and this will be, sorry, dt, yes. Similarly, on the y side you can do that integration separately, it will become a sub y dt, and this will give you the Vy. Actually, you are integrating the function which is given to you as a function of time, this will simply give you V sub y, right. So, once you have both Vx and Vy as functions of time, as a function of time, this one and also this one, you can carry out that integration one more time to get the x and y, or actually the position, the x and y components of the position vector. So, again when you integrate Vx with respect to t, this should directly give you x, right, and y will be simply Vy with respect to t, right. So, you have actually back calculated the x and y from given a sub x and a sub y, right. So, this can be another problem type in this topic, where acceleration is given to you, which means both of its x and y components are given to you, and you are asked to determine velocity vector and displacement vector. The summary is that you can determine both components of velocity vector separately, Vx and Vy, and then write the velocity as velocity vector as Vx times I plus Vy times j, right. You can carry out that integration again to determine x and y as a function of time, and then finally write the position vector r as x times I plus y times j, right. So, you will be using the same techniques which you learned in rectilinear motion, but now in x direction separately, y direction separately, to determine the x components of s, v, a and all quantities separately, and y components of the position, velocity and acceleration separately, right. Again, once you have in this type of problem, once you have x and y already as function of time, what you can do, you can eliminate time from both equations and finally combine both equations to get y as some function of x, right, and that will be the equation of the path actually. So you can again have in this type of problem also you may have a question type like determine the path equation or plot the path, right. So in order to plot the path, you must have an equation relating y with x or x with y, right. So if I summarize the whole discussion which I had up till now in just one sentence, that would be that rectangular coordinate representation of the curvilinear motion, rectangular coordinate representation of curvilinear motion is actually equal to superposition of the components of two, superposition of the components of two simultaneous rectilinear motions, and those both rectilinear motions or simultaneous rectilinear motions are in actual x and y directions, right, x and y directions. So what I am actually saying that a curvilinear motion when represented in terms of rectangular coordinate system actually becomes a case of two simultaneous rectilinear motions, one in x and one in y, right. You can treat the x component of displacement, velocity, acceleration separately to convert between them using differentiation and integration. You can treat the y component separately, right, and this is obvious in equation form also when you have derived these three equations. When you take the first derivative of r vector with respect to time and again another derivative of v with respect to time to get these three equations, you can see here that x and y motions are independent, they are separate, right. So when you have x, you do not have y in the same term, when you have y, you do not have x in the same term. You can independently convert x into x dot and then into x double dot. You can separately convert y into y dot by taking first derivative with respect to time and y dot to y double dot, right. So x component motion and y component motion can be seen independently, although the particle itself is moving in curved path, but we can decompose that motion into two rectilinear motions happening at the same time, right. So superposition means that I simply sum both components, right, superposition of the components or sum of the components of two simultaneous rectilinear motions in x and y directions, right. We have a vector sum of x times I cap plus y times j cap, right. So please keep those three equations in mind and I will end on that particular note, x times I cap plus y times j cap. Similarly, x dot I cap plus y dot times j cap will become your velocity vector and x double dot times I cap plus y double dot times j cap will simply becomes your acceleration vector. So you can conduct that conversion between r to v to a for x component independently, for y component independently. Same conversion can be done from a to v to r also by successive integrations for x independently and for y independently, right.